All right, in part two, we're going to pick up with titrations. All right, so let's grab a pen here and we'll jump right in. All right, so when we look at a titration, all right, let me go back a slide. There we go. We look at a titration, okay, we're going to take a solution of known concentration and we're going to add it to a solution of unknown concentration, acids and bases, in order to determine the concentration of the unknown acid or base, whatever it is. So let's look at this example we have here in the picture. So we have a known concentration of base, and we're adding it to an unknown concentration of acid. And we've got a pH meter in there, and the pH meter is going to tell us when we've reached something called the equivalence point. And so typically, like if we're using a strong acid and a strong base, like we are in this case, the equivalence point is going to be 7. So when we hit 7, we know we have an equal amount of strong acid and strong base. We could also use an indicator, and the indicator would change color as we approach the equivalence point. And once we know how many moles of base that we put in, right, because we know the concentration, we can use the balanced equation, right, the mole ratio from the balanced neutralization reaction, in order to figure out how many moles of unknown acid we have. And then since we know moles and we obviously have a volume there, we can do moles over liters and come up with the concentration. So that's how we use titrations. Now, like I said, when you do a strong acid and a strong base, the titration curve, which is what we have right here. So this is a titration curve. It's going to look like this. So our unknown starts down here at the bottom, right? So this is our unknown. And you can also kind of think of this as time is moving to the right, right? So each step to the right is time progressing. Now, I look at this graph and I can say right away, I'm using a strong base to titrate a strong acid. And I know that because the equivalence point is at 7. And I'm starting down here at a low pH, which tells me I have an acid. So when I look at the first part of this graph, we'll call this part A, or actually we'll use 2, right? Because that's what they used here, 2. All right, each time we drop a little bit of base in, it's reacting with the acid, but there's still so much acid present that the pH is not changing very rapidly. Now, as we get closer to the equivalence point, we see a very rapid increase in the rate at which these ions are being used up. And you'll see that it's very easy in principle to spot this, but in practice, it's very easy to go past the equivalence point, right? Because the rate here is almost vertical. It's almost straight up and down. And once we pass the equivalence point, we can see that there's still a slowing of the rate, and then eventually the pH doesn't change that much anymore. When you do a titration, you want to stop as close to there as possible. This is where we want to stop. All right, there's our stop sign. All right, if we end up here or we end up down there, then our math will be off by a little bit. So we always want to stop close to the equivalence point. Now, if we titrate a strong base with a strong acid, again, we're looking for a pH of 7, all right? But notice that my starting point is now high, right? And I can see right off the bat, that's a strong base, okay, because I have a high pH. And because the equivalence point is 7, I know that I must be using a strong acid. So we want to be able to spot or we want to be able to identify what's going on just by looking at the graph. So this would be a strong base titrated with a strong acid. Well, what about weak acids and bases? Well, if we have a curve that starts down here on the left, we know we have an acid, but our equivalence point is not 7, okay? It's not 7. So that tells me I must have a weak acid with a strong base, all right, because it's above 7 up here. And in order to kind of solve one of these, we're going to use some information we already know, right? We can use Ka to find the initial pH of our weak acid. The Henderson Hasselbalch equation will tell us where our pH is going to be in the buffer region, okay? And in this case, we have a pH, or we have an equivalence point where the pH is above 7. And so we can use the conjugate base of the weak acid to determine exactly what that pH would be. In this case, it says we're using acetate, so we must be using acetic acid. So we can use acetate to figure that out. Again, once you pass the equivalence point, you have a short region of rapid change followed by a nice slow tailing off. All right, there we go. If we have a weak acid titration and we want to be able to spot that, how it differs from a strong acid titration, just be able to identify these 3 things. Number one, the weak acid is going to have a higher initial pH than a strong acid. The pH change near the equivalence point is going to be smaller for a weak acid than it will be for a strong acid. And the pH for the equivalence point is going to be greater than 7 for that weak acid. So what do I mean by number 2? Well, look at the height of this curve, right? The relative flat area compared to the relative, vertical area of this curve. So it's shorter. So that's what number 2 means there. The pH change near the equivalence point is smaller, all right? We've talked about a pH meter. Let's talk about an indicator. What's an indicator? So an indicator is a weak acid, all right, that has, or sometimes a weak base, that has a different color than their conjugate base form does. So over a specific set range of pH values, that indicator will change colors. If you're trying to figure out the equivalence point for a titration, then the indicator will give you the range at which it is occurring. So phenolphthalein is a great example. It's a really common one. We used it last year in first year chem. So if you had me for that class, you've seen this purple indicator before. And the color change interval is 8.3 to about 10. And so if your equivalence point is between 8.3 and 10, then phenolphthalein is going to be a pretty good indicator, right? Like that's a good thing. On the other hand, if you want to do like methyl red for this same equivalence point, right, on this one over here, well, this would not be a good indicator because the range at which the indicator is going to change colors is outside of the range where the equivalence point is. So that's why we need to know the pH ranges of a couple different indicators, right? So that's, again, what this is showing. So in the first one, we wanted to use phenolphthalein, right? Phenolphthalein, yay, good. Methyl red, bad. In the second one, right, well, now my equivalence point is down here, so now phenolphthalein is not good, but methyl red is great. So depending on what reaction you're doing, different indicators are going to be more useful than others. Now here's another titration curve, but you'll notice that it has multiple vertical points, or vertical regions, and multiple equivalence points. So this is the case for polyprotic acids, so diprotic or triprotic acids. And each removal of the hydrogen ion is going to be associated with one of those vertical regions. You can also use the Henderson Hasselbalch equation here, and you can see that the halfway point to each equivalence point is going to give us the pKa for that step, which is an interesting fact to know, right? Henderson Hasselbalch for polyprotic acids can be used to find the pKa for the step. Remember, pKa is if you compare pKa and pH, you can determine if something is going to be protonated or if something is going to be deprotonated. So let's look at solubility. All right, let's switch gears a little bit, go to solubility. So ionic compounds are strong electrolytes, right? They dissolve completely, they dissociate completely, and that's what makes them a strong electrolyte. If you have an equilibrium equation, then the solid is the reactant, and the ions in the solution are going to be the product, right? We've seen this before. What's new is now we're going to take that and we're going to use it to write KSP. So we've had KA, we've had KB, we've had KW, we've had KEQ. Now we're going to have KSP. And KSP is going to be the solubility product constant. So let's look at one of these. So here we have barium sulfate on the left, which is dissolving in water. This is a weak electrolyte in this example because we have an equilibrium arrow. Into barium and sulfate ions. So the KSP for this is going to be barium times the concentration of barium ions, times the concentration of sulfate ions. Now remember, we always leave out pure substances in this, so the solid form gets left out because it is a pure substance. Here would be another one, right? We have barium phosphate. It's forming barium and phosphate. This would be Ba2 plus raised to the third power, right? Because we have a 3 coefficient right there, so we have to raise it. Here we have a 2, so we've raised it up right there. So that's our solubility product. Now, solubility and solubility product are not the same thing, okay? Solubility is how much of a substance dissolves to form a saturated solution. That's what solubility is. We use grams per liter or moles per liter to talk about solubility, okay? The solubility equilibrium is a different value altogether, all right? We can use it to talk about the molar concentrations of ions that are present in solution, but we're not going to be able to say like, X grams per liter because of the KSP. That's not how that works. So let's look at solubility and how we calculate solubility from KSP. And again, we're using an ice table. So this ice table thing, like we should be getting good at that. So the problem says the KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 Celsius. What is its molar solubility? So first thing we do is we write out our equation, right? CaF2 is at equilibrium with calcium ions and 2 fluorine ions. We write in the equilibrium expression, except in this case, it's our solubility product expression, KSP. Again, we do calcium concentration times fluorine concentration. Notice I had to balance and I had to raise the product there. And it tells me what KSP is. So I just plug that in. Now I go to my ice table. Well, the initial concentration of a solid isn't a concentration, right? We don't have moles over liters to give you a molarity, so you just use a dash. We know that at time equals 0, though, there is no calcium or fluorine ion present, so those are zeros. Our change in concentration is going to be plus X for calcium and plus 2X for fluorine because we have a 2 there. And so our equilibrium concentrations are going to be X and 2X. Now we need to substitute the equilibrium concentration values in order to get our KSP. So we say 3.9 times 10 to the 11th, negative 11th, equals X times 2X squared, which gives us 4X cubed. Solve that for X, we get 2.1 times 10 to the negative 4th. Now this gives us molarity, which is moles over liters. If we want to go from molarity to grams per liter, then we need to multiply by the molar mass. So remember, big M is moles over liters. So if we multiply that by molar mass, which is grams per mole, that will cancel and we'll be left with grams per liter. And there we go. So the question asks us for molar solubility, so we're good with leaving it in molarity. But if we want grams per liter to actually do the equation or do the lab prep, whatever, do it for real, we would need grams per liter. So that's how we get it. All right, a little bit of review, right? Factors that affect solubility. Let's bring the common ion effect back into consideration. So remember the common ion effect. It says that if one of the ions in solution equilibrium is already dissolved in the solution, the solubility of the salt that you add will decrease. So in this case, if calcium ions or fluoride ions were present, then we would expect calcium fluoride to be less soluble, right? So that's what we're looking at with the common ion effect. So let's look at one of those problems. All right. What is the molar solubility of CaF2 in 0.01 molar calcium nitrate? Okay, so what is different about this? What are we spotting? Well, in the first one, we just had it in water, right? We just, there is no common ion. But here, we've got it in an aqueous solution of calcium nitrate. And so calcium is going to be our common ion. And so that means instead of at time equals 0 having 0 for both ions, we actually have a little bit of calcium already present. And we know that the molarity is going to be that concentration present. So this box right here changes, which changes that box, right? The other two boxes don't change. When we solve this, we get a different number, right? We get 3.1 times 10 to the negative fifth. We solve it the same way, but we get a different answer because there is a common ion present. Now, there are a lot of other factors that affect solubility, right? Such as pH, right? If you have some substance with a basic anion, it's more soluble in acidic solution than it is in a basic solution, right? Your buffers are going to control your pH. So if you look at dissolving something into a buffer, and this is a common little thing they'll throw at you on the AP test. Remember, if there's a buffer present, you have no change in your hydroxide ion. So that would be affecting your ice table there. Let's look at complex ions. So metal ions, and we talked about this a little bit before in the acid-base unit. Metal ions can act as Lewis acids, all right? And they'll form complex ions in the solvent, with the solvent, that can basically become a solubility booster, okay? So when you see your complex ions together, like what's going on here? This is what we're looking at. So silver chloride is typically insoluble. Its KSP is 1.6 times 10 to the negative 10th. However, if you put ammonia into the solution, then the solubility will really increase because silver and ammonia can form a complex together. Well, how does that work? Well, here's silver and here's ammonia, right? And we know that ammonia has those two lone pairs. And so I can form a complex here and get this Ag, and it actually forms with two of them. You get a complex that looks like this. All right. And you end up with AgNH3 which has this nice little positive charge. Well, the moment that occurs, all right, well, now all of a sudden I can fit those chlorine ions in there and I can increase the solubility. So when you have complex ions forming, that is a metal reacting with the solvent in order to form these complex ions, expect the solubility to increase, right? That's how we're putting those two things together. What about oxides and hydroxides that are amphoteric, right? They're soluble in both acids and base. Well, keep in mind that aluminum, chromium, zinc, and tin, all right, are great examples of this. And so if you have like aluminum hydroxide, you can dissolve that into an acidic solution because you have an acid-base reaction going on. And if you put aluminum hydroxide into a basic solution, then you'll get a complex ion formation between the Al and the OH. You'll actually get AlOH4. So if you have some amphotericity there, expect an increase in solubility. Well, if we're going to talk about aqueous stuff, right, we got to bring around precipitants. So let's look at precipitants. So think way back to Q, right? When we calculate KEQ, but it's at some point other than equilibrium, we just call it Q. So if you can find Q and you can compare it to KSP, then you can determine if a precipitant is going to form. So there's three ways or three outcomes that you need to know here. If Q and KSP are the same, then the system is the equilibrium, the solution saturated, we would expect no precipitant. It would just be a uniform solution. If Q is less than KSP, then you can get more solid to dissolve. So you have no precipitant, right? You can put more solid into the spaces between the molecules. But when Q is greater than KSP, you will get a precipitant, right? So that is the relationship between KSP and Q, right? That's what we want to be able to do there. Now, you can precipitate, all right, things in the lab, right? But the most common time that we do this, I looked outside, it was snowing. I completely lost my train of thought. Let me restart this slide. Sorry. If we're in the lab and we have some unknown solution, and we know it's got some metals in there, or we suspect it has some metals in there, there is a set way that we can go through identifying what's present. And this is it. This little flow chart here. Now, normally we would look at this a little closer, but since we're in the virtual environment and you're just kind of reading along here, just take it to heart. there is a set method by which we can add specific known solutions in order to precipitate off certain salts. So if I have some unknown thing with some metal, the first thing I'm going to do is I'm going to add a little bit of 6 molar hydrochloric acid. And if I have any silver chloride or lead chloride or mercury chloride, that's going to precipitate. It's going to be insoluble. The next thing I'm going to do is I'm going to add some hydrosulfuric acid and a little bit of weak molarity or a lesser molarity HCl. That's going to give me all of my acid insoluble sulfides. They're going to come out second. So like copper sulfide or mercury, so all of the sulfides there. The next thing I can add is an ammonium sulfide mixture, right there, at a pH of 8. So I'm incorporating what I know about buffers. So I've got a pH of 8. And I'm going to add this ammonium sulfide, and that's going to give me all of my base insoluble sulfides are going to come out, and any hydroxides that are present. So things like aluminum hydroxide will precipitate, whatever. The last thing that I would do with my decanted mixture, right, of whatever's left, is I could add this ammonium species and some ammonium species, and this ammonia, and that will give me my phosphates. Anything that left must be an alkali metal, right? Because our alkali metals are typically soluble, and ammonium species, which are also typically soluble. So this is kind of the flow chart I would use to go through that. All right, so if you have any questions, let me know. I'll be glad to give you a hand, all right? But as we look at aqueous equilibrium, I know there's a lot here. So if you need to go back and rewatch a certain section, please do so. And if you have questions, again, please ask.